recording on this guy.
I guess because it is a webinar, it's a little bit different.
Okay, here we go. And I'm starting it. 3, 2, 1. It's live.
You're good.
Let's see what happens. I almost feel like I'm pulling this up on my phone to see like what would, you know.
Oh my gosh, we have 93, 100. We already
have
this. Almost 200 attendees.
Whoa! I can't believe. This is like the, you know, we released the app. How many people are downloading our app? Hey, we're making money. We're in the money. This is great. Welcome everybody dropping in for 61C. Oh, this is wonderful. Look at this number, 612. You have can everybody see the numbers too? This is unbelievable.
I don't think they can see the numbers. Only
they can't see the numbers. 680.
No, and they can't see the questions. They need
I know they can't see the
questions. Are flying.
Yeah. Oh, this is amazing. Great to see everybody. Hey, folks, write in the chat where you're from. That'd be fun. That'd be so fun to see all the places. Oh my! Whoa, it's too fast. It's like Twitch. It's like a Twitch channel. It's like this is amazing. Oh my goodness.
By the way, that's the reason why we are not pushing them to pushing the questions to the audience before they're answered.
Oh my! Yeah, you can't read it. You can't read it.
Yeah,
it's unbelievable. This is great. Great to see you all. Holy moly. 61C. This is amazing. This is great. What's the equivalent of having, you know, in the olden days, you'd ask your favorite students to sit in the front to make sure you have like your TAs. Hey, TAs, sit in the front. So that's what that was historically back at MIT, to have all the TAs sit in the front. What's the equivalent of Zoom? Like to do something? How do you get your special folks in? I just love this. This is great. Cameras on. Actually, can they? What's the view of students in a webinar? Can they see themselves? They can only see us, right?
No, they can only see the panelists.
Yeah. Okay. So they can see all the TAs there as well. All right. That's fine. Wonderful. Wonderful. That's just great. This is so fun. I hope you all are relaxing. Stephen just posted. You share. Feel free to unmute Stephen and share. We did post the slides, that PDF of the slides. We'll be going through this.
So I just pushed those to the website, so it might take a second for the website to refresh. And
yep. Oh, you only see me. Oh, that's good to see. They only see me for now because I'm spotlit, I guess. So that's fine.
Yeah.
Oh, it's 410. Ladies and gentlemen, 410. Welcome to CS61C. Woo! So happy to have you here. I'm teaching Professor Dan Garcia, my colleague.
I am Professor Nikolic, and it's a great pleasure to see all of you around here.
This is so wonderful. And we're going to break, I hope we break 1,000. We're at 825 if you can't see it. This is a delightful group. I've got my TAs, I've got a wonderful staff here that we're going to jump right in. We have a wonderful staff who are supporting us. Thank you for being here and joining. I'm looking here on the side for Q&A. Okay, wonderful. Let's jump in. So this is the introduction slide. This is an introduction lecture to 61C, Great Ideas in Computer Architecture, otherwise known as machine structures. Let's rock and roll. So here's the agenda for today. We'll think about machine structures. We'll talk about the great ideas in computer architecture, and then we'll talk about some red tape. This is a very different world. We'll talk about how we're moving this class online. Before I begin, I do want to reflect on the fact that many folks around the country, around the world, I know we saw the list of where people were from, are going through hardship right now. COVID's hitting communities. COVID's certainly hitting communities of color more than others. We've got smoke in some communities. We've got fire in some communities. We've got hurricanes on the East Coast. So I do know that people are going through different situations, and my heart goes out to folks who are struggling for this. We do have ways in this class. If you find that something changes in your situation, you need some help, please reach out to us, reach out to staff on Piazza with private posts is probably the cleanest way, because we've got 1,200 students. It's hard to handle all the email, but Piazza private posts is the way to do that. Please, folks, reach out if you need some support, if you need some extra delays, so that we can work with you guys. This is a semester. We're definitely going to be lenient and flexible that way. Also, I want to make sure you all know, vote. V-O-T-E. Please vote. Vote like your life depends on it, folks. That's another thing I want to mention before we jump in. All right. Here's the agenda. Let's go to the next one. So you're taking this class 61C. We're so happy to see. This is, by the way, the largest 61C in the history of Bora. Thinks it's actually bigger than just Berkeley. I'm going to say this is the biggest 61C in the history of Berkeley. Do you think it's bigger than that, Bora?
I am pretty sure this is the biggest offering of 61C in Berkeley, but highly likely this is the largest computer architecture class ever taught anywhere.
Ever taught anywhere. Ever taught anywhere. So, I mean, this is incredible. I'm just so happy to have my friend Bora and I and this great staff of TAs and tutors on our team in AIs. There's a lot of wonderful, wonderful people, almost all of whom have gone through 61C themselves. So we've got a lot of people who just love this class, want to give back. Lest
Hey, Dan,
you think, yeah, go ahead, Bora, jump in, go.
Can you say 2 sentences about yourself? How did you show up over here doing this?
Thank you for that. Wonderful. And I'll ask you for the same thing. So I was a grad student at Berkeley, and I fell in love with computer graphics, did a PhD in computer graphics, fell in love with teaching, joined the faculty, and then also when I was at MIT, my favorite class was the equivalent of 61C. It was called 6004. It was the digital logic class, and I loved it. So I said, I can't believe I'm at Berkeley getting to teach the class that I fell in love with when I was an undergrad. I actually got 2 majors. I got a double E major and a CS major at MIT. And so to teach this class actually does make that alignment. What brings you to this class, Bora?
Oh, I grew up in a country that does not exist anymore. It used to be called Yugoslavia. Now it's Serbia. I grew up in Belgrade, Serbia. And I came, actually to do a research project in the US at UC Davis. And that was supposed to be like 5-month research project. It has been 24 years since.
You got bitten by the bug. I love it.
And yeah, I've been at Berkeley for 21 years, teaching all kinds of things. This is the second time that I'm doing 61C with Dan. And although I am probably not as expressive as Dan, I'm as enthusiastic about the subject matter as he is.
I'm so delighted, Bora, to be partnered with you again. This is such a fun. We had such a great time 2 years ago, and I learned so much from you, and I hope to continue to learn from you. You are such a resource for us for the class. So we're really lucky to have you on our team. Thank you for that. So 61C isn't about C programming. If you came here thinking 61B is about learning Java, you were wrong. If 61A is about learning Python, you're wrong. Learning computer science here. This is about understanding the hardware-software interface. What you need to know as a programmer when you're actually going into your career at the lowest level. How does the whole thing work? How do you optimize your code? How do you make it fast? How do you make it parallel? All those things you'll learn in this class in a way that really was hidden from you from an abstraction point of view in 61B and 61A. So we'll talk about hardware. You'll learn how the entire thing works from the top to the bottom. This is the first class where actually you'll know from all the way at the top, the highest, most abstraction layer, all the way down to current flowing and electrons filling holes, all the way down in hardware. This is the only class that makes that connection. That's why it's so special, and I'm happy to be co-leading the group to make sure you understand that. So it's really great. You'll also understand how to peek below the hood and say, okay, this is the amount of hardware I got. Okay, yep, that, great. Here's how I'm going to adjust from the software point of view to make this program scream. So you got to learn how to make this stuff work in parallel in a way. And that's, again, thanks to a lot of folks who've taken this course before me. So I want to thank Nick Weaver, who contributes to a lot of the slides we're going to have. I want to thank a lot of folks who've helped us, Dave Patterson, Kirst Josinovich, John Morzanek, a lot of this wonderful, Randy Katz, a lot of our Kubi, a lot of our systems faculty have contributed to where this course is. So again, I want to honor them. We're standing on the shoulders of giants. We got an amazing systems faculty and architecture faculty and EE faculty in Berkeley. This is a picture of old school 61C. So we made a transformation of 61C at some stage, and this is old school 61C. And by the way, this photo is fake. And the reason we showed this is because we only focus on a single computer. A single computer, like that's all it is, as if a single computer with a single core. Like what? How are you still thinking about computer science and architecture and systems as a single computer with a single core? Crazy. This is new school 61C. Where you have more power in your hand and your watch and in your car and on your drone than people took to go to the moon years ago, right? It's unbelievable what you have as access. And the model, by the way, is that the front end, the interface, is now a personal mobile device. It's a car, it's a drone. That's the front end. That's the usable, and that's if you touch and see. But actually, that's the back end. Warehouse scale computing is where all of the stuff is happening. You type something in Google search, it's a little teeny line in your window, you think that's it. No, all of a sudden something fires up on some data center somewhere in another country maybe, and then feeds you the answer in a way you didn't even know. You say Siri, you say Alexa, all that stuff is being driven by these warehouse scale computer systems, warehouse scale computing. One of the things you're gonna notice in this picture, there's wind farms, there's water. We'll talk about all the details of how to actually make this work. We have a whole lecture on warehouse scale computing to see a little taste of that. This is what happens. You look inside. Look how cool that is. It's like the future. The future is here, folks. Unbelievable amount of energy and amount of engineering to make this work. So much work to get the coolant, to get this cool. Temperature is going to be a big theme here. So to keep this cool and to keep it the right temperature regulated, there's a lot of work. It's almost arguably more work there than it is in getting the bits to go around and do the right thing. It's really interesting. So this is the old school model. And this is a class, I've taught this class since 2004, and I happened to work with Dave Patterson in the first couple of years I did this. I learned so much from him. I've learned so much from all my co-instructors. I love co-teaching courses. So this 61C goes from the top level through C, through a compiler, through assembler, to machine code, through the instruction set architecture, big abstraction layer. We make that, all these are layers of abstraction, all the horizontal lines, but we color this one really big to say this is a big one. That's the software hardware boundary. Then the way we attack 61C is it's almost like a byte, the way you take an in and out byte. You're from the top down, and now you hit the middle layer, and now we're going from the bottom up. So now we're going to actually show you current and transistors and how to make a transistor and what you can build out of transistors, how to build basic circuits, how to make digital design, how to design these things, how to then take those big block elements and then make a data path and control that makes a computer work. And the computer you're going to make work is a computer that will interpret the machine code you compiled and assembled down to. So it's like the fingers will touch in a beautiful way. This is an amazing, this class is EECS actually. This class connects them in a way that no other class does, and I'm so pleased to be part of that. So it's great. So this is the new school machine structures in which your hardware is on the right. You've got parallelism at so many levels. You've got parallelism, parallel gates. That's the hardware description. Go from bottom up. I'll move my body here. Hardware description. All gates work in parallel at the same time. Now you have parallel data where you might chunk on more than one data unit at the same time. Then you have parallel instructions where you might actually be able to, Bor will talk about this in a second, have up to 5 instructions. You could even have more of that, but we'll teach you a machine that has 5 instructions at the same time. To have parallel threads. Now you're a little higher level software. Now you parallel threads. You've probably heard of threads before. Now you've got multiple cores. These threads might get assigned to the hardware cores and you'll run with that. Then you might have parallel requests where you do a higher level where you actually send off different programs doing things. And that might be parallel requests to do something. And you might have multiple machines wake up. Multiple machines are waking up serving that request. All of that is driven by a hardware and all that's driven by, so if you see the top picture here, you'll see that that's the inner workings of a data center, and all of those are based on a computer, which might have multiple cores. How does that work? Well, you have execution units, functional blocks, and logic gates, all that work on the hardware side. Pretty cool stuff. I'm going to pass it over to my colleague, Bor, who's going to talk about the great ideas in computer architecture. Go.
Thank you, Dan. Let's see if oh, look at this. I can control Dan's screen and Dan's slides. We picked a selection of 6 ideas that are great ideas, but there are many other ideas in computer architecture that are great as well. Here is a list. It's abstraction, how we abstract layers of computing and represent them such that the other layers don't have to think about gory details underneath them. The second idea is the Moore's law and the principle of scaling. The third one is principle of locality and memory hierarchy. Let me try to move myself. This then crashed. This is great. The fourth one is parallelism. The fifth one is performance measurement and this feedback of improvements based on the measurements and dependability and redundancy. The first one, Dan already touched on. This is a slightly different picture of the same thing. It's the idea that we would like to abstract every layer as we go through them, such that we don't have to think about how do gates switch every time we execute a new C command or a C instruction. So the idea here is to maintain all these layers of abstraction that pass relevant things up to the upper layer while obfuscating things that we really don't care about. For example, how the wires work inside a microprocessor. Second great idea is the Moore's law. Moore made this prediction long time ago in 1965 based on, really, if you look at this slide, there are only 4 data points, on that way, on that slide, 5 data points. And he noticed that over the first 5 years of semiconductor industry, the number of components per chip, essentially components or transistors, doubled in each technology generation. And he made a bold prediction that that is going to continue for the next 10 years. Well, he also, as a side note, he was a Cal alumnus and graduated not from ECS, he graduated from chemistry in 1950. He went on to found Intel Corporation after that. But look at that, what happened with Moore's Law over time. It didn't hold up only for 10 years. It held up for 5 decades after that. And it is still continuing, although it is slowing down. You have seen a lot of that in the news lately. We'll touch on that in a second. And there is a corollary over there, well, not directly related to Moore's Law. This is the A's Law. This is showing statistics in the US, what is happening with the grade inflation, basically showing that the number of A's is increasing in every year with a small trend. Well, if you continue doing this, going this way, by 2070 in classes like 61C and everything else, everybody will have A's. That's great news. Your grandchildren will all get A's. By the way, I mean, we are okay to give everybody an A this year. Help us out with that. We would find out experimentally what does the College of Engineering or Letters and Science do to us if we do that. But we would love to go through that experiment with you.
I think they'll celebrate us if we get to some stage where mastery learning happens and we take them all across the finish line. I think they'd love it. I think they'd love it. I think rather than being vilified, I think it will be celebrated. They'll say, how did you do it? How did you do it? Tell us how you rather than just do it for free. If they all got A-level material, if they all do well in the final, we give a same final, the same difficulty every year. If all the class gets above something and all the grades above, we give all A's. I love it. Let's do it. Let's make it happen. The first year ever.
Help us out. Wouldn't it be wonderful to break every rule in this college about the grading? Dan will talk a little bit about that towards the end. But help us out. We are open. This is a weird semester. Let's make it even weirder. The next principle is based on this beautiful picture that Jim Gray, Turing Award winner, Turing Award is like a Nobel Prize of Computer Science, and who Jim Gray got the bachelor's from Cal and a PhD. I think it was the first PhD in CS in Cal in 1969. He made this analogy of trying to visualize how far away is the data and how long does it take us to retrieve the data from different parts of a computing system. So on the left-hand side, what we see is a delay or a latency of how long does it take us to get the data from a different place in a compute system in nanoseconds from 1 to 10 to the 6th, 10 to the 9th. And then on the right-hand side, we have an analogy of how would it look like to retrieve a piece of paper or a thing from somewhere around us. So getting something from the registers that are on the microprocessor chip takes approximately a nanosecond. On the right-hand side, if that is an equivalent of a room or around, if it takes me to retrieve something from thinking about something, it takes me to get something from this room, would take me a minute. When we get back on the campus, if we need to get something, we forgot, I don't know, a handout on the other end of the campus and went to the class, it would have taken us 10 minutes. If we left it somehow in Sacramento, it would have taken us an hour and a half. Sacramento is an equivalent of going to the memory, going from the microprocessor chip to the DRAM chip, which is a separate chip on a computer motherboard. If we need to go to a disk, to a hard drive, or even a solid-state drive, that is like going to another planet. Going to a magnetic disk is like going to Pluto. Going to a solid-state disk is, kind of going to Mars. Not a big difference from that standpoint. And then finally, if you need to somehow get to a tape or an optical robot that is doing backups, well, that's like kind of going to another galaxy. All right, so that's what is important. What is important there is understanding this principle of locality and memory hierarchy. If we look at this, if we look at this, what we have is this principle of locality where there is a lot extremely fast memory that is available on a microprocessor chip that is extremely expensive and has tiny capacity. And as we go out away into the caches, into the physical memory on the board, which is DRAM, and down to solid state drives and hard disk drives, in every layer, the amount of memory there gets by about an order of magnitude bigger, by about an order of magnitude cheaper, and about an order of magnitude slower. What we'll see, these compute systems are built, what we're going to be doing with building these compute systems as we go through them, to make user see memory as infinitely big, infinitely fast. The fourth
abstraction, just got to say it over and over and over. The most important idea of this class is abstraction. That whole slide was about abstraction. You live at the speed of the small, fast guy, but you actually get the abstract view at the sizes of the bigger guy. I love it. Thank you, Bora. Perfect.
Thank you, Dan. Yeah, then the fourth idea is that we'll be drilling in through various views of abstraction, and else is the view of parallelism. Dan mentioned parallelism a bit already, that many things in compute systems are happening concurrently. So this is the first one. We're going to drill into this. This is a complicated picture showing execution of a pipeline processor where 3 instructions are concurrently being executed on a processor in time slot 3. And we don't need to understand that now. We are going to go into gory detail of that. There are different ways how this concurrency can happen. Another one is this idea of thread level parallelism. For example, we can run multiple software threads through a compute hardware, through a computer, even if we do not have multiple execution units, for example. Where does that come from? While we are busy going to, for example, to Andromeda to get our next batch of data, we can run a complete program through it, or multiples of them. That's a principle of running multiple threads on a microprocessor. The third way how we can see this parallelism is, this is an old illustration from the times when people still used paper folders. So if you have a bunch of folders that showed up on somebody's desk that need to be urgently processed, you give them to multiple people. And these multiple people, Anna, Ben, and Chen, can sort them in parallel if it is the same algorithm that they need to perform. This is a principle of data level parallelism. There is a caveat in there that stands behind, is a principle. It's the basic message of Amdahl's law. Amdahl says this, that the longest pole on the stent will always stick out. So if we have a large amount of parallel code, for example, in our program, say 50% of parallel code, that means that the other 50% of a code is serial code. If we try to parallelize to infinity this parallel code, that means that the total speed up is only going to be up to 50%, because now the serial code is going to be the bottleneck. We'll be seeing this over and over in compute systems, the principle of the longest pole. We will always work on squishing something that we can accelerate and make fast, but then we have to worry about the other things that pop up. Now, the fifth idea is the idea of performance measurement and improvement. That is one of the things that Dave Patterson, our emeritus, has spent a lot of time in his early career in trying to quantify the metrics of compute systems. So the idea here is we would always like to match the application hardware, to match the application to the underlying hardware to do things that we care about. So we would like to exploit locality, we would like to exploit parallelism, we would like to build some special hardware features. But this is something incredibly important going forward from now on. Now, important thing about performance measurements is we do want to metricize what we care about, and that is often latency and throughput. So when we talk about latency, that is how long does it take to complete a task. What is the throughput? How many tasks can we complete in a given amount of time? But things that matter over there are also how long does it take us for these highly parallel tasks? How does it take us to wind up? How long does it take us to fill up the queues? And then how quickly we run through the full queues. And remember, latency is all about the time to finish the tasks. The sixth important idea is about dependability and redundancy. And the picture over here is something that is going to get us even if we take care of everything else. This is a picture of a cloud chamber. We had a video of a cloud chamber. Now we can't run it through this kind of a Zoom application that we are running. The cloud chamber basically records hits of cosmic rays onto the Earth into this, so we see some ionization happening there. These little traces that we see on the slide are essentially charged particles that are hitting a chamber over there. They hit us all the time. They hit our chips. So even if we build everything redundant, these things are going to rain on us. And they've been raining since the Big Bang on everything that is out there in the space. They have a tendency or ability to flip bits, and bits, that used to be zeros may become ones. Those that were ones may become zeros, and that's not going to look good on, for example, on somebody's bank account, especially if one gets flipped to a zero. So many of these compute systems need to be made very dependable in that way. This is now really popular topic when we talk about self-driving, because there are certain standards that these systems need to meet there. One of the basic principles there is the redundancy. And that principle of redundancy says that a failing piece doesn't mean that the whole system will fail. In this case, if we ask 3 processing elements, what is 1 plus 1? And if 2 of them think that the answer is 2, one of them thinks it's 1, well, we can vote what is the right answer, even if it did not know what is 1 plus 1. And we can use this majority vote to determine what is the answer. That is one of the basic principles, how compute systems have added reliability to them over time. One thing, consequence of Moore's law, is that we have very many transistors nowadays. One thing that we do with that is we can use them to do redundant computation. Here are a few examples of how this is being done. One thing that some of us did not know, that there are redundant data centers in the world. Dan has shown a picture of a data center out there. And Amazon runs data centers in different parts of the world. If there is a power outage, Amazon doesn't go dark. If there is a storm, if there is a fire, Amazon doesn't go dark. The next thing you might have heard, there are redundant disks and RAID systems, which basically means redundant arrays of independent disks. If you basically have a system of 5 disks, it allows you for 1 disk to fail, and you continue working like all of them are there. And another example on the bottom of this is a DIMM, which is a DRAM device that gets plugged into a computer. It is there to represent 8-bit words, but look, there are 9 chips. One of them is redundant.
I should point out that our colleague Randy Katz was one of the leads of the RAID project. So a lot of the things that you're learning were invented at Berkeley. In fact, we're going to see in 2 slides how people have been honored for things invented at Berkeley as well.
Yeah, we are a little bit, we do tend to invent a lot of things and reach to take credits for those. Now, a couple of slides here is something that is very interesting here. The computer architecture has become the most exciting thing out there in the computing, at least in my opinion, but I'm not the only one. Aforementioned Dave Patterson claimed that this is the golden age of computer architecture. Why is that so? Well, compute systems went through the waves, and these waves, we have seen 3 waves so far. The wave of mainframes, that was a long time, like when Dan and I were little kids. There were mainframes that were used for scientific computing and big data processing made by IBM, and they would take a whole room. There was a revolution of personal computers that came in the 90s and exploded with the development of the World Wide Web in the 90s. It was replaced by the era of smartphones, and the killer app there was the app itself. We are on the tail end of that wave. It is being replaced by a new wave that is very amorphous, and we don't know exactly how it looks like. There is a whole bunch of other things that are important there, and they're happening. That involve healthcare and telemedicine and education, autonomous driving and gaming, entertainment and VR and AR and all kinds of other things that require, in order to be efficient, require to be implemented specialized systems. Now, because of Moore's law slowing down, this becomes an architecture issue. What we find out, machine learning is a common for most domains nowadays, but it is not the killer app. The killer app is to make the car drive. Use the machine learning to make that happen. This is another another slide that shows how things have changed over time. We have gone through a lot of Moore's law, 5 decades of Moore's law. And now if you look at the latest points on this chart, on the top curve that is showing the number of transistors, essentially doubling every 18 months or every 2 years, depends on which part of a slope are we in, it is slowing down. It is still, we are still getting more transistors, but they are not coming that easily and that abundantly as they did before. So the other thing, power has been limiting many of the chips. So in order to limit the power increase, otherwise we would be running little furnaces in front of us, the frequency had to be limited. Single thread performance was tied to the frequency. In order to get better performance, we went parallel. So we saw the number of cores increasing. But what has been observed now, there is a limited amount of parallelism that is out there because of Amdahl's law. So what do we do now to get more compute performance? That's the idea of specialization. That is why we are seeing, a lot of development of these heterogeneous differentiated systems for different compute domains. An example here is Apple A13 Bionic that has, multiple microprocessor cores on it, and then has specialized units like GPUs that will find graphics processing units, and now has a neural processing unit and a whole bunch of things that are unlabeled here. Apple does have an event tomorrow. They are interested in hiring a lot of people because they want to capture a lot of domains out there. So check it out. They may tell you something about CS61C and how much they care about that class. Now, trying to wrap these ideas up, where are we now and where are we going to? All conventional wisdom involved basically this Moore's law giving us a free ride. Every year or every other year, we would get a better computer. So no matter how bad our software was, it would just naturally run faster the year after. So some people say that was that led to the education or development of lazy programmers. People who just basically, it did not make sense to work a lot on your application. It didn't make sense to develop custom chips because it, you can just wait for a year while instead of you're sweating and developing something new, a new custom chip. Well, your general purpose processor is just going to get better and everything is going to get to run faster the next year. But with Moore's law slowing down, this is not the case anymore. So we need to build specialized computers. This is Google's TPU version 3, which was publicly released only last week. Interestingly, that was at Hot Chips conference. And it was showing the details of what you have there. So this is showing a top view. What you see on the top is a top view of a TPU 3 board that has 4 liquid cooled chips. That thing, when put in the racks, that can deliver over 100 peta floating point operations per second. That's a very large number. That's something that was completely unthinkable and will not be reached by general purpose computers for a long time. You need a specialized computer for that. Now, to wrap up what Dan has started talking about, Dave Patterson and John Hennessy 2 years ago won the Turing Award, the biggest award that exists in computer science, for essentially developing many of these principles and writing them in a textbook that we are using, that we are covering in this class. So with that, I'm going to hand it over back to Dan.
Wonderful. Thank you so much, Bora. Thank you so much. One of the things that Patterson and Hennessy did was they went against conventional wisdom. If the world said this thing, the world said we have to have complex instruction sets. We'll teach you what that means. And they said, no, I want a reduced instruction set, much more simpler instructions. The hardware is easier to build. They said, they would be laughed at. They were laughed at conferences. They would be like a panel, and they'd be on one side, and the CISC people, the complex, would be on the other side, and everyone was on the other side, but they held their own, and they were right all along. We go back, they were right. It's like some people were right all along. So this is that was certainly well-deserved and certainly honors some of their foresight that they had with regard to the path of this. Let's talk about what you need. Let's talk about some red tape. So I'm a huge Star Wars fan, huge Yoda fan. Baby Yoda, can't wait till the next season comes out. And so this is the worst Yoda imitation ever, but it's always in motion the future is. So that is the idea that who knows what's going to happen, who knows when storms and smoke and all these things. Our schedule may change slightly depending on factors, and this includes everything, lectures, assignments, and labs, but we'll try to keep it as much as we have, but we'll also let you know as soon as we know something's going to change, we've got that going. And we're also trying a lot of new things, and we say, well, we promise this, but then we had to back it off a little bit because things might go down, the server might go down. Well, we need to practice on this, and we need to hopefully get a stable system for you, and we know it's not stable, we'll pull it off and go somewhere else. So overall, let's just some course information, just some basic red tape here. The course is called 61C. The website is called 61c.org. Thank you, Stephen, for doing an amazing job of making it look really, really usable and accessible and dark mode, and it's awesome. So some wonderful web designers are part of that team. Bora and I are instructors. Please call us Dan and Bora. Don't call us Professor something. It's Dan and Bora.
Never.
Yeah. That's what my mom calls me, Professor Garcia. Anybody calls me Dan. I'll even correct you if you call me anything other than that. So call us that. We have an amazing group of teaching assistants, and I was going to get out of this, but I'm stuck. The C webpage was when I was going to get out and show the thing. There's a wonderful webpage. Maybe Stephen, can someone add the link to the list of TAs? I can encourage people to look at the list of TAs. We have a wonderful staff, TAs, tutors, AIs. We're going to add as many pictures as we can to that. A lot of people are here as part of our panelists to support us. Amazing group of folks. I want to thank them all for their service to the department, service to this course. We would not be able to teach this course without them. It's just two of us and there's 1,200 of you. I got 911 participants here. This is the biggest course I've ever taught, ever. And we have an amazing staff this year. We worked really hard. The head TAs can know we worked really hard to pick the best folks to be part of this based on experience and passion. And we think we got all of them. So we're excited about that.
Just one thing to add.
Jump in.
Our complete teaching crew, whole teaching crew, has approximately 100 people. Just think about that. It's a typical computer architecture class.
Got a small army.
In a normal university,
managing a small army. It's unbelievable. In fact, we were so big that last year there was no room on campus that would hold us. In fact, we're already too big for any room on campus. Biggest room on campus is 800 in Wheeler, already too big for the biggest room on campus. So we actually this is the first time we ever have everybody in the first lecture. It's pretty exciting. So 9, 10, 9, 11. And hopefully more people will be able to come into other sessions. Our textbook, we have 3 textbooks, Patterson and Hennessy. We showed you the picture before. COD, Computer Organization and Design. Make sure you get the RISC-V edition. There are other editions there, and you can get some cheaper there, but make sure you get the RISC-V edition. KNR, this is the classic. Every C programmer ever, I'm going to say ever, has the KNR second edition on their shelf. There's a big cyan C on the front page. Make sure you get that one, not the older one. Borivoje and Halsey, I'm not sure if I'm pronouncing that right, has the data center as a computer, and there's a new 3rd edition. So we're going to have the new version up there. I think we might have the old one still linked, but we'll get the new one. Well, we'll need this like week 12. You don't need this till now. Piazza is where all the action happens. Our community is getting together, our 1,200 people happening on Piazza. Every announcement, discussion, clarification happens there. Even pinned, threaded posts where you can respond. We've really, our TAs have thought about how to actually manage Piazza really well. They did a great job with that. Let me do kind of an old school, new school. This is what we used to do, okay? Many of you, I don't think anybody here is a freshman, but if you are, welcome. To be able to take 61C your first time freshman year, that's impressive. Maybe that's 1 or 2 of you in the group. I think there was somebody years ago who took 61A, B, and C first semester. I think that actually happened once, and they got all A's and blew my mind. This is the old school on the left column, the new school's on the right. So lecture, obviously Monday, Wednesday, Friday for an hour. If you miss it, you can watch a video. And many people, by the way, over time decided, you know what, I'll just watch a video. And so, 61A used to have 1,200, now it's over 2,000, and they taught in one classroom. And they said, it doesn't matter if the classroom only holds 800 because not everybody's coming anymore. And there'd be 200, and then 150, and then there's the stalwart 100, and they're all spread out. Nobody even sits in the front. They all sit spread out. This is before you had to have 6-foot distancing. So we used to be able to fit into Wheeler. Never for the first day, but in general. But anyway, the point is we had that. The new model is Bora and I want to bring community together. We want to share what the week is like. We want to talk about computing in the news. We want to talk about how to set you up for success. Give you little announcements, like announcements. We want to do that. We want to be able to share the John De Niro announcements line. So all that happens during these live lectures. They're going to happen 1 time a week. Usually it's Monday. If Monday's a holiday, it's going to be Wednesday, okay? So we want to make sure just to bring the community together. Our TAs will be here. Our staff is here to ask any questions. This is a chance for us to get us live action, okay? That's lecture. We all have recorded, and we're in the process of recording all of our content lectures into little snippets, into little like 8, 10, 12, maybe if it's a little, sometimes longer, 20-minute snippets. After each one of those is going to be a clicker question. Those clicker questions are credit. You will try it. If you get it wrong, there's no penalty. You just keep trying it till you get it right. It's like a lock. You have to get it all right till you get it right. Once you get it right, you get credit for watching the video, okay? So that's the idea. These clicker questions are kind of a way to force you to do this. And you're going to have a couple days after lecture to do that. Every snippet is, roughly, as I said, 4 to 20 minutes or so. So you watch this and then have a question. Whew. Lab. The way lab used to work was, we had 2-hour lab. You'd done in pairs, typically TAs and AIs circling to answer any questions. You get a checkoff at the end. And those are also meant to be done for credit, meant to get full credit for that. Just like your lecture, clicker questions meant to be for credit. But there was no clicker questions for the live lectures, only for the content lectures. Now, here's the idea. You and your partner will do them together. You'll find a Zoom room. You'll find a partner in Piazza. You'll find a Zoom room. You can also come to lab office hours. We'll have people, we'll have staff ready to support that. When you're all done to get checked off, you either get checked off in the lab office hours or you'll get checked off in this 13-minute checkoff spot. This is the only required face-to-face interaction. So actually, we try to be supportive and flexible for this online space. If I can't make lecture, we're filming every lecture. We've already pre-filmed the content lectures and we'll be filming these live lectures done. If you can't make the lab, you only have to show up once a week, meaning you can't just page out and asynchronously take this course. The only one thing you have to do is show up for the checkoff spot. 13 minutes, you and a partner. It's the time for our students, our staff will support you. We're going to find out, how are you doing? How is the class going? Are you ahead, behind? It's a time to get some human face-to-face connection. This online world with 1,200 students is just so hard to do this. We have some discussions. It's so hard to have some face-to-face. This is the time for that. So you have to have this checkoff spot, have to have a how's it going spot in the 13-minute checkoff spot. That's our chance to find out how you're doing. Discussion typically was an hour. It happened at the end of the week where we summarize the week and we maybe have a worksheet that drives everything. The same thing's going to happen, but we realize, you could watch the videos to do that. If I give you the worksheet and say work on it, and then we have a video of our TAs doing the worksheet, giving the solutions, you can get just as much benefit. So we're going to, but we encourage you to come to the live discussion. So we're going to have 3 of them, only 3, 1,200 people. We would have had 40 sections. You know what? We're going to take our staff and actually focus on those checkoffs, that face-to-face interaction. That's where we're kind of taking the currency of all of our staff and pouring it into the face-to-face small group learning and the checkoff and the how's it going space. So discussions, we've got 3 sessions spaced all across the day. Those are going to be video recorded. So you can watch those if you want to. They're all the same material, but you can just see different people attack the material different ways. And we're going to have our pre-recorded discussion videos you can watch. All those are just resources. We'll give this to you. So that means if you work with, if synchronous learning works for you, you can do synchronous. Come to lecture live. The content is still pre-recorded, but you'll come to lab live, you come to discussion live. But if you actually, because of some situation, you can't do that, no worries, we got you covered. Watch do it on your own, and then get the checkoff in lab. You have to at least be face-to-face with lab checkoff, and you can also just watch the discussion video and watch the lecture video. So all those things will be great, and yes, the discussion videos will be recorded. We also have other parts of the course. We have office hours. Drop in office hours gets questions answered. We're going to have that as well. We typically have TAs typically run the majority part of the office hours. Those are called conceptual office hours. I'm confused about parallelism or caches or whatever the topic is, and they'll kind of like HCAN office hours, like that. There's also office hours that are not conceptual, but about help me get through this project. I'm working on it. I'm stuck. How can you help me with? And there might be some, I got this bug, and then the TA might be teaching you how to debug. They're not going to just not going to say, it's line 47. That'd be the worst TA ever says line 47. The best TA is, teach me what you're thinking about. Tell me what you were asked to do. How did you know it was wrong? They're working with you to teach you how to debug it so that you find it yourself. We don't want our TAs to give the answer out. That doesn't teach you how to fish. We want to teach you how to debug it so you can solve the next problem you have. So the way we do this online is we're going to have the same kind of thing. Again, lab office hours online on Zoom, project office hours for those, and regular office hours, which are regular for anything else. And that'll typically be as I said, either conceptual, and there'll also be a faculty office hours. So I'm going to have two times, and Bora can talk about what he's going to have. I'm going to have a general office hours for everybody just drop in. And I used to be able to have 13 chairs in my office. Now I can have 1,200 if you want to drop in. It's going to be a time where I'll typically do kind of a summary of stuff. I'll say, well, look, next week we've got an exam. Let's look at some exam questions. I might pull out some exams. We'll do them together. It's really great. I also going to have, if you want to talk to me personally, privately, one-on-one, I'll have some individual slots you can sign up for. And obviously I don't have an infinite number of those, but you can grab some infinite time if you just want 10 minutes to talk about something in private. That's always, people used to do that back in the days. They say, Dan, can we walk outside? I would walk outside my office and have a private conversation. I'm going to have sign up times for that. So we'll do that. And those are all going to be during the same slot. Monday, Wednesday, Friday, 4 to 5 is 61C slot. And my slot's going to be group office hours on Wednesday, and sign up office hours are going to be on Friday. Exams. In the olden days, okay, Bori, what are you doing for office hours, my friend? You want to talk about that?
I'm just going to do the mirror review.
Yeah.
The general one on Friday, sign-ups on Wednesday.
Perfect. Love
We'll
it.
try it out that way. If we need to modify, we'll modify. We are here to help. One thing I wanted to put a pitch for these Mondays, so we know what we're doing on Wednesdays and Fridays. I really would like everybody to get together for these Monday meetings. We're doing something special. Dan and I put an effort to bring guests from outside. Don't complain later that you missed it.
Don't miss these.
Some of these do not miss guests.
Yeah.
I keep them
We're
as
not telling you in
cannot...
advance. They're all surprise people, so you got to come and you won't know until you get there, because we want to keep these a surprise.
Yeah, we can't publicize that we might break Zoom.
Right. Good stuff. I'm going to record my general office hours, Bora. There was a question on the Q&A for that. I'm going to do mine. There's no reason I
should do that too.
Yeah, we'll just go in over problems. So that'll be that. I'll say, anybody have any questions? I'll try to summarize some stuff, and I'll try to do reteaching of that, which would be great. But we only have 5 minutes. I want to make sure we get out because I think chemistry is right after us. So the way we're going to do exams is a little different. You're going to be given 24 hours, and we'll give you an exam. It's going to be a randomized exam. You know that's kind of the new software we're using now, and you'll get a new copy, and you'll be able to use all open book. Never done that before. Open book exams, love that, but closed internet. You can't search it. You can't talk to your friends, and we're going to ask you to take your cell phone. Here it is. And you can't see my cell phone. You're going to take and make a time-lapse video. You put it so your cell phone can see over your shoulder, see your hands, see your screen, and you say, go. Make it a time-lapse. Time-lapse means it's just much shorter video. Then you take the exam. When you're done, you stop it, you submit the exam. So that's the way we make sure that cheating isn't happening. We keep it all honest. That'll be it. I got, I think, 7 slides to go through in 5 minutes. So let me go fast.
Dan, pin yourself. You can't see. It's pinned to me.
There we go. No worries. Right. Thanks. Okay. Course grading. We got 4 minutes. Here we go. Go to Dan mode. Here we go. Lecture, lab, homework, projects, quest, There's some exams in there. There's some sprinkle points for being a good citizen for APA on top of that. And there's also going to be a performance competition. So there is some place. You have to give some extra credit for that. 4 projects, awesome. The first 2 are individual. The second 2 are partnered. And you've seen, labs and homework. So labs are check off. Lecture, that's the clicker quiz we talked about. Homework is there and projects are there. The grading policy, we're absolute graded. We're not curved. We want you to work together, collaborate, teach each other. This is the space. This is an amazing space. I believe curving is evil, where you can't, 100 people, all the students get A's. No, you can't, because you're not allowed to get all A's. Why? That's crazy. You can't give all your students A's if they've done it. So I think curving is not the right thing to do. We've been absolute grading for a long time. Job internship interviews, the material, whatever grade you get, the material you learn in this class is the most important. You know what the most important class is for your interview? Huh? CS70. We know the second most important class for your interview? 61B. But the third most important class for your interview is 61C, and we're sticking by it, and we think it's great. So we love this class. We think you're going to learn a lot from it. It's awesome. All right. Our goal as instructors is to make the greatest course ever. We want to be 7.0 HKN instructors at the end of the year. We're trying to give all these pro-student policies, humor, enthusiasm, technology, guests, touch on the news, guests, fun and challenging programs. Hopefully you really love these projects and you really learn from them as well. Pro-student, we have exam clobbering. Other classes don't do it, I do. You learn it later, you can override an earlier exam. We love that. We want to be that. Give us feedback. Let us know how to improve this class. All right, 2 minutes. APA, if you're a good student, come up to office hours, complete all the assignments, turn in your homework 0, ask great questions in Zoom, make it an interaction, do the performance competition, help others in lab and Piazza, write some software, do some other thing that's out of the box that teaches people. Boom, all those things are ways that you can get altruism credit. Help people on Piazza is another way, and ask questions on Piazza. That's kind of an easy way to kind of measure those things. All right, 1:30. We have slip days. You know that we typically have slip days. We have 3 slip tokens, not slip hours, not slip minutes. You can slip an assignment and you can use these 3 tokens either all at once or save them till the end or one at a time when you need them. This is an important thing. Please read this slide. All projects aside from, actually this is updated, aside from the first and second, I'm sorry for not updating that page, will be done with a partner. So third and fourth is with a partner, first and second are solo. You cannot, obviously you can't cheat. Don't share material. Don't have a public GitHub repository. Anybody who gives the material is equally responsible for someone who gets the material. All those things are bad. We have caught in the last several semesters 50 to 100 people, and we prosecute all of them. And we will do it again this year. So don't do it. Take a step back if you're thinking you're doing this. Ask for a slip take. Talk to us. We would love to say, Dan, something's going wrong. I got some COVID, smoke, whatever. We will give you some special things if you need this semester because we know that online is weird. Do not cheat, folks. If you get to that point, please do not. Take a step back. We made it. In summary, 20 seconds left. 61C is about 6 great ideas of architecture. Bora burst through it. Does a great job of covering these 6. The whole semester is revisiting this and hitting these 6. We'll see it over and over and over. Bora, take us out with some thoughts.
One thing, you said everything great. One thing that we didn't put on PowerPoints, there will be prizes for the best performers in projects.
Yes, yes.
Apple will tell us tomorrow that CS61C is one of the classes that is on the prize list. Whoa!
They're excited. So please do that prize. Please do the performance competition. There's chances for actual physical prizes. We'd love to have that. Folks, we are so happy that you came. I don't want to go too much over, but we're so happy to come 61C. Ladies and gentlemen, 61C. Woo! So happy you're here. We're going to have a great year. We got a great staff for you. We will see you on Monday. Have a great weekend, folks. Go. Woo! Good job, everybody. And stop the live thing. How do we stop the live thing? Anybody for all? Let's see. Stephen, how do we?
You're in control.